Thank you all for being here. Wow, this is a lot of people who are really interested in debugging production microservices. And it turns out that this is a very important problem to think about. Why? Well, it turns out that 40 to 90% of the total cost of ownership of your services is after you're finished building it. You will spend 10 times as much time debugging and running your system in production as you will building it. Think back to this morning, to the keynote, right? Where it was described where Wilk said, I could spend an entire lifetime debugging bugs in my own system, right? And our systems have gotten so much more complicated since then. So it's really important that we be able to understand what's going on in our systems in order to make sure that our users are happy. So why are we here today? So I'm from the Google Cloud Reliability Engineering team. And we focus on teaching people who are potential cloud users how to build and operate reliable systems. Because if we don't teach people this, people are not going to feel prepared to run applications in the cloud. And then they're going to be unhappy with the reliability of their services. So this is not a vendor pitch, right? Like, I want to teach you how to be successful in the cloud, because this is where the future is.
Similarly, I'm here because I'm actually, unlike Liz, relatively new at Google. I've only been here for about 18 months. But I've been in the space doing SRE and DevOpsy type things for about a decade now. But the most remarkable thing I realized when I joined Google was I was working with much, much bigger systems, more complex, more replicas, more everything. But they were actually simpler to debug. And I realized this was not because of some magical Google thing they have going on, but because of the techniques that they use. And there was nothing specific to Google about those techniques. So I'm hoping to share some of those techniques with you so maybe your debugging can become a little bit easier too.
So let's suppose that we have a service. How many of you in the audience, raise your hands nice and tall, are you running microservices? OK, that's almost everyone. That's good. How many of you are running microservices running on dozens or hundreds of different replicas? Like hundreds of different replicas. OK, some of you. At least dozens? How many of you have at least dozens of different machines that you're running across? OK, good. So the idea that we ran into at Google was that we had an explosion of metrics, that we had an explosion of cardinality that was caused by the fact that we were collecting a lot of different metrics about every single job that we run, and that each of those jobs was running on hundreds, thousands of different hosts. And as a result, it was difficult to get to the right data that we needed. For the purposes of this talk, we're going to assume that you're doing latency-sensitive user query serving. There are other approaches for batch serving, but that could be an entirely separate talk. Let's also talk about how we monitor our systems, how we detect failures in our systems. I usually assume when I give this talk to an audience of SREs that people are using service level objectives. But I know that many of you here are not SREs. Raise your hand if you know what a service level objective is. OK, that's about 10% of the audience. So let's define it. So a service level objective is a way of measuring whether users are able to successfully use your service. And you can design your systems such that the only alert that you have is on that one metric. Are your users able to use your service or not? Because it turns out everything else is just noise. It doesn't matter. Does it matter if your hard disk is 90% full and it goes to 90.001% full and an alert fires? No. As long as your users are serving queries, you're fine. So the idea behind the service level objective is that we need to define what user happiness looks like and measure it at the highest possible level. And then if there is a problem, we'll get alerted and start debugging through the stack to figure it out. But even if you aren't using service level objectives, you can still get value out of this talk because it will teach you how to debug the unknown knowns in your service that you haven't set up explicit monitoring for. And maybe our hope is that it will persuade you to switch off some of those alerts because you know you will be able to debug problems using the techniques we described. If you want to know more about SLOs, again, that could be an entirely separate talk. But I do have a 5-minute talk that is recorded on video. That's the QR code on your screen. So you can watch that afterwards. So let's suppose that we have our running microservice system, and something goes wrong in our system. And this is at Google. What happens? Well, our users start experiencing errors. And then our service level indicators start failing, either the ones that are set up on error counts or the ones that are set up on latency, that those values become unacceptable to us. and we start burning through the budget of allowed errors that we allow ourselves to have in our production systems, knowing that we can never really achieve 100%. So that means that our service level objective that we set is in danger, and that pagers need to go off and SREs need to be woken up. Now what do we do as SREs? We prioritize the speed with which we mitigate the problem and recover from the problem to restore service as fast as possible. So what does this look like? Well, we can kind of think about this in terms of a loop of how we debug our problems. So we start off meeting our service level objectives, and then a fault happens somewhere in our system. And then we get woken up, and we have to quickly figure out, how big is this problem? Is my entire service down? Is 100% of my traffic serving errors? Or is it a smaller problem that I can take my time resolving without dragging in additional people? Can I do something quickly to mitigate, like draining a bad region? If so, then I'm going to do that first. But after that, I have to go and start figuring out what's going wrong with my collection of microservices. So the way that I go about this is I think about what could be going wrong, right? Like formulate a hypothesis as to what is broken. And then I'll test it. I'll figure out, is that actually what broke? And hopefully, I've identified the right cause to begin with. And then I can go ahead and figure out a fix, and I can test the fix, and then hopefully I go back to meeting my service level objective, right? So everything's happy. But unfortunately, that's not usually where I spend the majority of my time. Because it turns out a lot of the time, when we develop a solution, it's not the right solution. Or when we develop a hypothesis as to what we think is broken in our systems, that's not actually what is broken, and we're back to square one. So we wind up spending, as site reliability engineers, or as anyone who is on call for a service, we wind up spending a lot of time in that loop of formulating hypotheses and testing them. So how can we make our systems more resilient? How can we make them more reliable for our users? And how can we increase our velocity with which we're able to experiment and push features out to users? The way that we can do that is by speeding up that loop, by formulating hypotheses faster and testing them faster. In decision science, this is described as the OODA loop, the observe, orient, decide, act loop. So today we're going to work through a set of practical examples using 3 best practices: LayAppealing, dynamic data joins, and exemplars. As a note about the technologies that we're showing you today, we're showing you Google's internal monitoring system, which is called Panopticon, which is a front end for Monarch. These are Google's internal technologies, but the techniques are fully generic. You can implement them and take them home with you and do them today. We'll name public implementations, both open source and vendor supplied. And we're also going to mention that some of these features are already present in Google's particular implementation in Stackdriver. So Adam, you're on call, and your pager goes off. Beep.
OK, here we go. This is sort of a text version of basically what I would receive when my pager goes off. It's not the most helpful thing, but because all of our alerts are based on SLOs, all it's telling me is one of these SLOs is in danger. We have a service level indicator of how fast, the latency of our queries, and it looks like there are too many of them which are not meeting that objective. There are too many slow queries. It's telling me that the SLI is being violated in US West 1, the region US West 1, because we only have regional SLOs on this imaginary service. There are a lot of different services which are running inside of US West 1, some of which are in different zones, but we don't actually have zone level indicators. So all that this alert is telling me is that something in US West 1 is essentially too slow. Now, this could be caused by all of the replicas in US West 1 being slow, a little bit slow, or it could be one replica which is being very slow. All it means is some percentile of our queries are being served too slow. So I'm going to dig in and try and find out exactly what's wrong. First technique I'm going to use here is called LayAppealing, because as I mentioned, all of these SLIs, they're composites. We're not going to set off an alarm every single time one of our replicas gets slow, so we have to merge all of those together somehow. And then when we want to find out what's going wrong, we need to peel back those layers. So first I'm going to start, let's show a diagram. first I'm going to start looking at the region which is going wrong. I can disregard US Central and US East 1 because those aren't paging me right now. I'm going to dive into there and find out which zone is going wrong. And once I've isolated that, I'm going to drill down into the individual replicas. So this is roughly how our imaginary service is architected. So here's Pecan. There was a link or Panopticon rather, we call it Pecan internally. There was a link inside of the page that I received, which takes me to this page. And you can see pretty clearly what's happening here. We have a constant line at 100 milliseconds, which is our SLO. We promised that within a certain region, thank you, within a certain region, all of the queries are going to be, well, 99% of the queries are going to be served below this line. So the fact that this red line has gone over this constant means that I'm getting paged. And this happened a couple of minutes ago. So the first thing I do is pop out the sidebar. Panopticon, it's a very interactive tool. It's roughly our internal equivalent of something like Graphite, but it's much more deeply integrated with the back end. So as you can see, the query which is being shown on the screen now, which is representing the metric which paged me, is actually editable. If we zoom in a little bit, we can see that there's a filter on it because we have all of the data for all of the regions, of course, but there's only one which is paging me. So Panopticon has helpfully filtered all of the other regions out. But as Liz mentioned, the very first thing that I need to do is establish the blast radius of this outage. It's possible that this is the first region which is paged, but all of them are on the way up and the rest are going to page me soon. So I can remove this filter. Now there are no filters. And if we look back at the chart, now we can see that all of the regions are plotted. Now, one of them is clearly in danger, but the other two are basically fine. I don't see any kind of problem there. So that's a relief, and I'm going to filter them away. Oh, oops. Sorry, I skipped forward a few too many slides there. What happened? So, obvious question. Why don't we just look at all of the streams straight away, all of the streams that make this composite SLI? Because if we did, it would just be a complete jumble on the screen. There's no way that I can discern any kind of useful signal out of this. The whole point of this exercise is to turn that jumble into one stream where I can identify that this is the actual problem. And you can see on the right-hand side there, if we look at the key, each one of these different streams is representing a different replica in a different region or zone. Each one has its own latency metric. So if we go back to bisecting, we're now showing the problematic region again. One of the really cool things about Panopticon and about Monarch in general is that these are aggregates that we're looking at now, and these aggregates are computed behind the scenes. I'm not doing a big query here where I'm taking the latency metrics or latency streams, all of the latency streams in the world, and aggregating them at query time. They've already been aggregated for me. And it's a little bit like a materialized view in a SQL database. And I know that Influx calls these standing queries, but we call these precomputations internally. We have query evaluators running behind the scenes, which just do these queries all day, and then rather than outputting to the screen like we are now, they're just outputting to another metric, and then that metric is the one that alerts me. So I'm looking at the output of this precomputation right now, but I want to drill down. So I've highlighted this link we have, replace with the definition. And essentially this replaces in line the query with the query which behind the scenes was run to generate the query that I'm seeing now. If we skip back and forth, you can see the line itself, the data, it doesn't change at all. It's the same data, of course, because one was derived from the other, but in the query editor on the left-hand side, now I've got a lot more control over my query. This query is a little bit slower, not noticeably slow, because we're pulling in more data and rendering it at query time as opposed to doing it at precomputation time. But this is cool because it means I can modify it, which is what I'm going to do. Look at the very last one.
The other thing about precomputations is that it's a level of abstraction, right? It kind of lets you form libraries. Remember the talk from this morning about libraries, right? If you can make parts of your monitoring queries libraries that you can pull into other parts of your monitoring queries, that reduces the amount of detail that you need to keep in your head at any given time. Yeah. Look at how much more complex this query is.
Yeah, this is much more complex, and this isn't even the raw data. We're still looking at a precomputation here, which we're going to drill down into further. But if you look at the last I guess, operation in the query editor, it's a group operation. And these group operations are essentially like SQL group operations. We take a lot of streams, and then we output a smaller number of streams by aggregating the input streams in some way. When I'm looking at this, the chart here, this is grouped by region, because we only want to see it by region. But I want to see it by zone now, so I can go down to the bottom and group it by zone as well. And now the output will show me the aggregated latency of all of the replicas in each of these zones. Now you can see one of these zones is looking totally fine. One of them, really interestingly, is above our regional SLO, which you may think, why isn't this paging me already? But we don't have a zonal SLO in this imaginary service. We don't offer any guarantees about how fast individual zones will be, only that within a region, 99% of all of the queries will be less than 100 milliseconds. So that's why that didn't page me. But you can see one of these lines very clearly is going up. It looks like we have some kind of problem in this region. So we're going to drill down into that. If we pop open the sidebar, we can see which zone this is in exactly. It's US West 1A. So let's focus on that. We're going to go back to the other sidebar, and we're going to add another filter. So this time, we want to throw away all of the input data except for the replicas which are in US West 1A. So we've done that. And if we scroll down to the bottom, at this point, we could keep drilling in, but I want to show you something really interesting, which is often the first step that I take when diagnosing these problems. The very last step here is transforming, if you can see the types of these queries, they're wedged in between the operations. One of them is a distribution, because we measure a lot of things with distributions. Latency distributions, that is. And the very last item is a double. It's just a number, essentially. And so the last step is transforming this distribution by taking the 98th, I think, percentile and transforming it into a number. Now, we have to do this because the distribution itself is very hard to interpret. It would be very hard to write a rule on that distribution to alert people, or for a machine to evaluate and to alert people. But this is pretty easy for a machine to evaluate. It's a number. If it gets too big, send me a page. Easy. But when I'm debugging, I want to look at a bit more detail. So I can remove, by clicking on this little cross, the last operation. And now, the output of this query is a distribution. So the way that Pecan renders this, I think, is really cool. This is a heat map. And I've deliberately, I've made it lower resolution than we would usually look at, so it's a little bit easier to understand here. But essentially, the black area at the top, or the left-hand, the y-axis, I guess, represents the latency, of course. It's the same as the previous chart. And the y-axis, or x-axis rather, represents the time. So you can see at some point, this heat map started to extend upwards. The black area at the top essentially means there are no queries which are within this latency. Earlier on, 5 minutes ago, there were no queries which were taking 140 milliseconds. But now there are some. Like, we've crept up and we can see those lines which are overlaid. The 50th, I think, 90th, 98th, and 99th percentile have started creeping up. And so now there are some number of queries. Not a tremendous amount. It's really only affecting the top few percentiles, but there are some of them. But what's really interesting is you can see the bottom of the heat map. It hasn't changed at all. The vast majority, the 50th percentile, are still basically where they were. So we're not looking at a situation where the whole zone is slow. And you can imagine why that may happen, some kind of network contention or something. But we're not looking at that here. We're looking at a subset of the replicas inside of this zone are serving slowly. So we're going to drill in a little bit further. Back to the line, again, we're going to replace this definition. Now that we've focused it on one zone, we're going to replace this query with its definition to look at all of the replicas in this zone. And I think we can pretty clearly see what the problem is here. Most of our replicas are behaving as normally, but two of them, the 98th, I think, percentile has gone through the roof recently. So let's assume at this point that there's something wrong with these replicas. We skipped a slide here, but if we hovered over one of those lines, we would see that the replica ID of this was 4, one of them. So we're going to add another filter. So now we're looking exclusively at the latency metrics which are coming out of replica 4 in US West 1A. Again, we look at the bottom operation in this query, and it's a distribution to percentile, or distribution to double operation. And we're going to remove it, so we're looking at the heat map. This is the raw distribution of latency coming out of that one metric. And this is really interesting. We're not seeing the same heat map as we were at the zone level. We're seeing quite clearly that where previously our 50th percentile was around 60 milliseconds, it's gone through the roof. In fact, there are now very few queries coming out of this replica or being served by this replica which are being completed within 100 milliseconds at all. So this replica is completely broken at this point. So I'm going to go ahead and restart it and hope that solves the problem. That would be a good stab at mitigation. I'm optimistic. So that's LayAppealing. LayAppealing is really helpful in situations where some kind of aggregate of a signal which is being emitted by a very large number of targets, or let's say replicas, is causing an alert. And you need to drill down or bisect into that to find out what or which replica is causing the problem. But of course, much of the time when we're dealing with microservices, there are far too many to just start by looking at all of them. You need some way of intelligently drilling down, and that's LayAppealing. But that isn't always the case. Sometimes it's not so much that there's one task which is going wrong, or some number of tasks that have something in common, like their location. Thank you. There's some other cause, some other quality that those replicas have that where there is no path between the alert and the actual problem. You've got to form a more elaborate hypothesis, and you've got to pull together data to figure out what's wrong. So just to illustrate that, we may be being alerted in one region, but actually the problem's kind of everywhere, and there's no clear way to like drill down and find out what is the problem just based on that one query. So we're going to have to join it with other queries, and we call that dynamic query joining. I would open up to, if I were to, let's imagine that my first solution did not work out at all. There were no replicas which I found which were at fault. I would open up a new tab in Pecan, because I'm going to make my own query, because I have a hypothesis about what might be wrong with this. I remember a few days ago there was some kind of, I overheard the kernel team talking about latency, so maybe I'm going to look into that. I'm going to look in my service, and I'm going to pull out a totally different metric. All of our jobs or tasks that we run at Google export, as Liz said, a tremendous number of metrics, one of which is the kernel version. And it's worth noting that I know not all microservices do this. Not everyone runs on a standardized code base where you have all of these useful metrics coming out all of the time. But I urge you to, because it's great.
Yep, use Envoy or any other service mesh, because it'll give you lots of these out-of-the-box metrics.
Absolutely. And then even though I'm not going to alert on my kernel version, of course, but when something's going wrong, then I might want to join that data back to the error signal that I'm getting to see if I can diagnose what's wrong. And that's what I'm going to do here. So I've pulled up the kernel versions of each of my different replicas. There are quite a few of them, too many to be useful. But I am going to, if we were to zoom in on one of those rows, we would see each of those rows has all of the standard information about it. It means that for each replica, we export the region, we export the zone, and we export the kernel version it's running. In this case, it's 1111. So I'm going to create a group by operation. Rather than editing queries which are being given to me by my pager, I'm now creating queries from scratch. So I've added a group by, and I've grouped these by version, and I'm using a count reducer. So essentially what this means is, given all of those streams, I want to see one stream for each different kernel version, and I want to know how many of each of those streams have that kernel version. And this is how it goes. It looks like we have about 138 running on version 1111. And some of our older versions, we have a few stragglers running down there. One is as old as 1002, which we have, coincidentally, 2 tasks running as. So if I jump back into the latency metrics that we saw before, these were completely indecipherable. As you may recall, we had to drill into them to find out what was wrong. But I can take these metrics, and I can join the kernel version onto this to make something which is more useful. I've joined these, and if you see in the query visualizer on the left-hand side, we've essentially taken this query, the latency, and the previous query, and we've joined them together. So rather than dealing with 2 separate queries, we're now dealing with one which outputs a tuple containing the latency and the kernel version. You see on the right-hand side, we've still got all of those streams for latency, but we've augmented them with the kernel version. So now we can do something clever with this. We can group the latency, we can take the mean latency of each of those different kernel versions. Because again, I have a hypothesis that this might be related. And what do you know, it is. One of these kernel versions has a mean latency which is much higher, and it started about the same time as the other kernel versions. So if I pop open the sidebar, then yeah, it's this straggler kernel, which for some reason is still rolled out in production, which is exhibiting a lot higher latency. So at this point, I don't know, maybe it would be a good time to firstly kill those jobs to mitigate the problem, but secondly to maybe file a bug and say, hey, why are these old kernels out? Maybe we could set up some kind of non-paging alert based on old kernel versions, as now we know that they're causing problems. But honestly, it's a different talk, really. The summary of dynamic data joins is you don't necessarily have to export every single piece of information which might be useful. We call them tags or labels, or I guess internally we call them target fields, but I've heard them referred to as tags and labels. if you were to export every single one of those, for example, the kernel version with every single metric, you would be completely overwhelmed with these useless data. What you can do instead is export this data from each of your tasks without necessarily alerting on it, and then later on at alert time when you're debugging, you can join it back together at query time and derive a lot more value from it. So that's dynamic data joining.
So you'll notice that Adam has spent the past 10 or 15 minutes telling you about how he might debug problems, starting kind of from first principles, starting from the top of the stack, working his way all the way down to the bottom in fine-grained detail. But what if I told you that I could beat Adam to debugging the problem
Surely not.
by using a really cool technique that we developed called Exemplars? The theory behind Exemplars is that if you have high cardinality data, like individual task-level data, or you have distributed tracing turned on in your systems, that you can use sampling. You can probabilistically keep small amounts of that data around, and that you can use that data to jump directly to where your problem is, rather than having to repeatedly bisect to find the problem in your stack. Now, you can do this with any kind of graphing tool. In fact, I know that Lightstep has implemented this inside of Grafana today, and that other providers such as Honeycomb also have it integrated into their UI. So you have to mark in your distribution graphing tool which individual buckets have samples associated with them. And then you can highlight which samples have the same tags, so it will let you more easily cross-correlate the problem, and then potentially go off into Zipkin or your tracing tool of choice in order to get the fine-grained details. So let's walk through what this might look like. So essentially, what we have is this is the same system that I was showing you with LayAppealing, except for I have a tool that will let me say, hey, by the way, replicas 1 and 3 are bad. That's where your high latency is coming from, just with one click of a button. So what does this look like? So let's remember, back when we were debugging the problem where we had a few tasks that were slow, although I didn't know it at the time, and we were trying to figure out globally, kind of where is this rise in 98th percentile latency coming from? So what I can do is I can, inside of the group by, where I would normally throw out all of the task level data and say, you know what, I don't care that it's task 1, 2, 3, or 4. All I care about is that it's in US West 1A. But I can say I want to retain some of the task IDs. So if I do that, what happens? What winds up happening is that suddenly I get a bunch of little green lines over here. I know it's hard to see on a conference projector, but I see a bunch of little green lines indicating that there is data associated with each of those buckets. And if I click on one, it will highlight all the other buckets that share the exact same tag. So if I click on it, it will tell me, hey, by the way, Liz, that task that is slow is task number 4. And that'll let me jump directly to the task that's failing and start investigating or maybe mitigate by killing it in the short term. Right? So what took Adam about 10 minutes to bisect took me 20 seconds to look at because of the availability of this fine-grained data inside of my distribution graphing. Here's a real-world, non-contrived example. We have many machines running at Google, so many that I can't tell you. And we need to keep track of, for instance, how long does it take each machine to reboot? What was the current boot time on the most recent reboot? And as you can imagine, retaining the task level data for every single machine at Google might be very expensive. But if I only keep one example for the most common values, say 100 seconds or 80 seconds to boot, then that lets me focus on the outliers and retain the task level data for those as well. And there will be much less duplication of that data. And I can go and click through and find out, hey, that one machine is slow. I should look at the logs to figure out why it rebooted slowly. But let's talk about tracing as well. So in the case of tracing, how do I make this useful? This is an example from the team that I used to manage until 2 years ago. So this is the black box monitoring system where we've said we care about the write latency as performed by the black box prober. And we've told it, hey, by the way, sample 1% of the queries that you issue and send them to Dapper, our tracing system. Zipkin is the public equivalent. So I can go and look here because, say, for example, I've just gotten paged. And what I can see is I can see that on one hand, I have overlaid here the 99th percentile line, right? Like it's this little purple line that's weaving its way jumpily up, right? And so I may have gotten paged an hour ago, and I'm staring at this, right? And the number one thing that I see when I look at that graph is, wow, that's a lot of queries at X thousand milliseconds right here. That's a lot of queries. And that even was happening before I got paged, and there just started being more and more of them as time went on. That's an example of your percentiles lying to you, right? Your percentiles don't tell you that. You really need to have distribution bucket heat maps to be able to see stuff like this that gives you useful hypotheses about what's going on. So I say to myself, OK, I want to find out what's going on with those X thousand millisecond traces. So let's go and look at one sample trace. So if I click on the little T symbol that I have highlighted, it'll give me a link to go directly to the Dapper or Zipkin trace. And then I can see and expand out the trace to find out what were all of the calls made throughout all of the various microservices in the stack. And what this happens to tell me is that the microservice dedicated to distributed file system operations, called Colossus, that process of finalizing files is repeatedly taking X thousand milliseconds. That sounds an awful lot like some kind of timeout, right? That gives me a very useful starting point for saying, OK, now I know exactly what dashboard I need to look at. I need to look at the distributed file system performance dashboards and at the file closing and finalization flush metrics, right? And then I could potentially even overlay them on the same graph or do some kind of other join according to what Adam was demonstrating right before me. So how do we do this? The way that we do this is that we collect the data in high fidelity, and we decide what to throw out later. So every single job running at Google has the monitoring library built in. If you were to use a service mesh, right, then you would get all of that stuff built into your service mesh. And it exports the streams into a collection service. And then when we aggregate the data, when we actually try to query the data, that's when we can say, you know what? If there is more than one example for that bucket, for instance, if I have 2 traces, I only need to keep one of them. Or if I have two different tags, 2 different like individual replica level data, I only need to remember one of them. And that lets me go ahead and make sure that I have this fine-grained data stored alongside my aggregated distribution. So as an example, right, like inside of my client, I might say if I'm inside of a trace context and I'm supposed to be sampling exemplars, then hey, by the way, as I'm storing data inside of the distribution, go ahead and record that trace ID alongside it. Or hypothetically, actually, no, this is a real example. YouTube uses this. If you can imagine, every single video ID encoded by YouTube, right? Like that thing on the end of the YouTube string, you know, ID equals foo, right? We can't possibly store a data stream for every single video that we encode or transcode. But what we do instead is that we record a bit of custom data associated with the latency of every single video recording and encoding request. And that way, when we're looking at the distribution to see what videos were slow to encode, I'll be able to see a sample video ID for every individual latency bucket and for every individual slice of time, which is pretty cool. So when it gets time to deduplicate, right, when I'm figuring out what to throw away, the core concept is that we do a weighted average, right? That if there are more samples associated with a given bucket from one source and fewer from another, then I'm going to weight towards retaining the higher level, the more granular data from that source that's present more often. So I do the weighted average, and then I store only one of them, and I throw the rest of the data away. So with the example traces, or with the example tags associated with a problematic thing, or anything that I want to investigate in more detail, that's displayed alongside my graphs, that gives me much easier tools to form hypotheses about what's going on in my system. Like maybe I want to go directly to task number 4 and go look at the logs at a specific timestamp because I know that I will find a slow query there. So I still need to be able to do the dynamic query building and joining and evaluation, but it lets me take a lot of the time out of bisecting because I'm able to jump faster to these solutions by keeping a small amount of the sample data around. So like I was mentioning earlier, this is present in Lightstep. This is present, I believe, in Circonus. And this is also present in Honeycomb. So there are many providers that already provide this, and this is coming soon to Stackdriver as well. So to wrap up, we improved resiliency by reducing the amount of time that it took us to find problems in our system, that we formulated hypotheses faster and tested them faster. And we did this using the 3 techniques: LayAppealing to bisect the problem, dynamic data joins in order to find correlations between our data, and exemplars to be able to more quickly jump to examples of things that are failing. Of course, after any incident, it's always important to be able to record what did you do, how did you arrive at the results that you came to. So for that reason, we typically add critical queries that we use into our playbook. However, I discourage you from adding them to your dashboards as a knee-jerk reaction. Why is that? Well, it turns out that storing extra dashboards and pre-computing extra queries has a compute and storage cost, but that's not even why I'm concerned. What I'm concerned about is the cognitive overload of having too many dashboards. This is a problem that I see way too many teams jump into. They define a dashboard for every single thing, and what you wind up doing when you're on call is you look at the list of 50 different dashboards, each with 50 different individual queries on them, and you can't make heads or tails of it, and you spend 20 or 30 minutes just picking random graphs to stare at. Did that graph wiggle at the same time as that other graph? I'm not sure, right? Like, there's a huge cognitive cost to adding dashboards.
Much of the time, those dashboards are going to be leading me in the wrong direction as well. It's just because a dashboard is wiggling, if your SLO isn't in danger, then there's really no reason to be looking at it.
Yeah, so no 2 outages are identical, so it's important to figure out what are the common patterns that you can use to generically debug any outage, and what are the things that are specific to that one outage. So we reduce time to resolve and spend less error budget, which means that we can spend that error budget instead on pushing our code out faster. And the way that we do that is to be able to do ad hoc queries, to be able to write our own monitoring queries, to look at the data, to play with it, to drill down. You really don't want to build 100 different dashboards. And instead, if you are able to quickly and confidently root cause things, you're going to have a much better time running distributed systems and operating in a microservice environment. So I urge folks to take a look at OpenCensus, which is an interoperability layer between many different monitoring and observability tools. And you can read more from my team at cloudplatform.googleblog.com. And in particular, I really encourage people to look at Jana's blog post about observability, which talks in a lot more written detail about the concepts that we described today. So that is our talk. And you can also read the Site Reliability Engineering book today. And 2 new books are coming out this summer, both in early access on O'Reilly, the Site Reliability Workbook and Seeking SRE. Thank you so much. And I think we have time for about 5 or 10 minutes of questions.
Thank you.